There we go. Okay, so today we're going to finish up talking about recursion, and then we're going to start into the last big topic of the semester, which is trees. And we'll spend actually about 3 weeks talking about trees before at the end we tie things up by revisiting big O notation. So basically today I kind of want to do 3 things. I want to finish up the Sudoku problem from last time. There's just a couple of loose ends. Then I want to quickly go over one last example with recursion, which is the Towers of Hanoi. And finally, we're going to get into trees today. Start doing an introduction to them. And there's actually not very much that I need to say about the Sudoku solver. There was just one thing that, well, a couple of things. First of all, I wanted to re-emphasize what Dr. Planck was doing with his, when he was checking the valid rows. So let's get that right here. That what he was doing was taking advantage of the fact that characters can be treated as integers, and he was actually using a vector here that had 58 elements in it, and the first, I believe it is 49 of them were empty, and then at 48, that is the character representation, I'm sorry, 49 is a character representation for 1. 57 is a character representation for 9. So he was just making a calculation here that wasting some space wasn't a big deal. That the trade-off was some ease of writing the code and ease of readability versus wasting some computer memory. And this is an important issue. Sometimes it's worth trading off some computer efficiency to get code that is easier to read or easier to write or easier to write and therefore less prone to bugs. Yes, Alan?
I talked about similar structures a few times in labs because they've come up in the solutions and talk better and stuff. And I also mentioned in lab how it's an example of a hash table where you don't need to do any hashing, so you get all the benefits of hash table algorithms.
Right. Without so I'm guessing you treated the vector as like a hash table, but you made it awfully big, but that way you could just directly use the numbers to get into it without having to apply a hash function, or
Yeah.
Okay, yes.
Which is what this is, right?
Yes, this is what this is. So you just, as you get more experienced, you will kind of start to get comfortable about when it's right to make this kind of trade-off. Here, he's wasting about a little less than 200 bytes of memory. Okay, so the first 48 or 49 entries aren't used, so there's about 50 unused entries. Integers take up 4 bytes, maybe 8 bytes, so he's wasting between 200 and 400 bytes. That's nothing on today's computers. Okay, but then the other thing he had to be careful about, and he was when he did the constructor, is that when he created this checker, find Sudoku 3, he had to make sure that he didn't just resize it to be of size 10, he had to resize it to be the character 9 plus 1. And the plus 1 is because we start with zero-based indexing, so he needed that extra memory location for index 0. So that was the other thing he had to be careful about. Now the third thing about this is, think I'll throw this out to you for a moment. Why do you think that he made, back here, why did he make this checker vector be an instance variable when you can see that he could just as easily made it be a local variable? So he certainly could have simply here said vector int checker. Okay, and he could have made it of size 9 plus 1 there. And he could have simply put 0 like that, and then he wouldn't have even needed that statement right there. Okay, because it's clearly a local variable in the sense that you don't need it. You're always initializing it to all zeros, and then when you're finished with the routine, you don't need it anymore. When you check is column valid or is panel valid, you just reinitialize it. So why do you think he made checker be an instance variable rather than a local variable?
So he didn't have to keep remaking that huge vector.
Very good. He made it an instance variable rather than a local variable so that he would avoid, so Dr. Planck avoids constantly reinitialize or reallocating memory by making it an instance variable. Avoids constantly reallocating and reinitializing memory by making checkers or making checker an instance variable. So in this case, Dr. Planck kind of went the other way in the sense that it probably would have been a little more readable if he had made his checker vector be a local variable. Because the way the code's written, you don't know by looking at the code what checker is. You would have to flip. Let's say you were maintaining the code. You picked it up from me, or you picked it up from Dr. Planck, and you need to maintain this code. You've never seen it before, and you look at this routine, is row valid, and you see this strange checker object. Well, you have no idea what it is, so you're going to have to go flipping through code to figure out what the heck this checker object is. Whereas if you declared it locally, you wouldn't have to flip anywhere. You would know immediately that checker was a vector of ints. And flipping through code involves what's called a context shift. Okay, when the brain makes a context shift, you lose focus for at least 15 seconds. It takes at least 15 seconds to re-engage the problem, okay, and to pick up your train of thought. So that is a blow to programmer efficiency. But this is a win for computer efficiency. So it's just, again, yet another trade-off where in this case he chose to sacrifice a bit of readability for computer efficiency. Okay? So these are two different examples of trade-offs he made in opposite directions in the same code. Yes, Alan?
A couple of questions. Instance variables are synonymous with class member?
Yes.
Okay.
Yeah. Okay, the reason I'm saying yes is because class member, to some people, is going to have the connotation of a so-called class variable, which we haven't really talked about, where it's shared among all instances. Yes. So I try to avoid the word class member because there's a little bit of ambiguity there. Okay?
The other question also is, would it have the same effect effect if you declare it locally to that function, to that method that made it static? Would that also avoid it being reallocated?
Yes, it would.
And that would get the benefits plus the readability, right?
It would get the benefits plus the readability and a little bit of extra space because you'd have one for each of the three methods. But yeah, that's actually a good compromise, Alan. I don't think we've really talked about that though. So just don't worry about it. But for those of you who kind of are interested in gimmicks, there is you could have done this, and this is what Alan is talking about. Again, don't worry about this if you don't understand it. But when you declare a local variable static, it actually does not disappear between invocations of the function. It actually is saved, typically to a global area of memory, place where constants and other things are stored. And the state information is not lost for that variable. Instead, when the function re-enters, whatever state information that variable had is retained. So this is actually an example where you might declare it as static, and then you could have it as a local variable. As Alan said, now you have the benefit that someone coming in and reading the code automatically sees what checker is, plus it only gets allocated and initialized once, which is the first time the function is called. Mark?
So would that be on the stack or the heap?
Neither. So that's what I was saying. When I was saying that these static variables, there's actually a third part of memory. So there's the stack, and there's the heap. Okay, and then there's a third part of memory, which is where the program code is stored. Okay, because somewhere the program code has to be stored, right? And in that area, there's actually some memory for things like global constants, global variables, and these static locals. Okay, because these are things that stick around for the lifetime of the program, but they don't get any new allocation each time you add a stack frame. So this static variable, all instances or calls to the function share it. So it doesn't go in the stack frame, it doesn't go in the heap. It's pre-allocated in this special part of memory right here that's kind of bundled with the program code. Okay, so there's really three places in the code, or three places in the program where you might find variable definitions or variable storage for variables. Okay. Now again, I won't test you on this. This is just something you may wish to store away as something cool. Okay. Other questions about it? Yes.
So so I know with like testing in general that generally you want to stay away from static types. Why is that? What do static variables do things best?
I don't think that they do anything bad other than that they're a danger with recursion, because recursion tends to imply you have a new copy of your variables each time. So like in this case, I think there's absolutely zero wrong with it. Okay? Okay, I'm suspecting that this is a bit of a religious argument. Okay, sometimes we talk about things where people get real strong on one side or the other, and because I've used them before, I've never had an issue with debugging with them. Okay, Mark.
And especially for like static class members, you can run into issues where different instances can change the value.
Right. Yeah, but generally those would be declared constant. It's rather unusual to have a static class member that's writable. Yeah, that maybe that's something that there I would agree with Mark that having non-static class variables is kind of bad. But again, we haven't really talked about so-called class variables. And I'm referring, I guess I've been referring to these types of variables as instance variables. And we also called them member variables in 140. I think, Alan, you probably have been calling them class members.
I think I have.
That's okay.
Now you're saying non-static. You're saying avoid non-static class.
No. If so, static. If you declare, if I declared this vector here static, it would turn it into something that we call a class variable as opposed to an instance variable. It would mean that it was shared by all instances of the class, and there would be only one copy of that variable rather than each instance having one copy. And we haven't talked about that really.
There's no such thing as a non-static class.
Correct. No such thing as that. What I meant is not, I probably misspoke. I meant to say non-constant. Okay. Non-constant class variables are dangerous because, as Mark pointed out, any instance could modify it and that change would automatically occur to all other instances, and that's dangerous. But don't worry about that. That's just kind of a additional thing. Okay. The other thing I wanted to just quickly go over, because it might not be totally obvious, is you'll remember that we had 3 validity checks when we set a number in the grid. We wanted to make sure that a row was valid, the column was valid, and a panel was valid, meaning when we changed a cell, we wanted to make sure that the panel to which the cell belongs is still valid, has no duplicates. And there's a slight issue there of determining which panel we're talking about. So it's pretty clear, let's see, which row and which column we're talking about. So if we change a cell, let's do that. So if we set grid RC to I, it's pretty obvious which row we need to check for validity. It's row R. And which column we need to check for validity is column C. The only thing that's not so obvious is which panel we need to check. And this is the code that Dr. Planck uses for checking to see which panel we are part of. So the key observation is that panels are 3 by 3, right? So we have in a Sudoku puzzle, we have 9 such panels. They start at row 0, row 3, and row 6. Because they're 3 by 3. And similarly, they start at column 0, column 3, and column 6. So if I give you, say, R equals 5 and C equals 4, just eyeballing it, you can figure out that we must be in that panel right there, right? R equals 5 and C equals 4. Do we agree with that? But we have to, in order to check the validity of the panel, we have to find the boundaries of the panel. So we can see that the boundaries are some multiple of 3. So we have to get back, in this case, to the start of this. What is the beginning coordinates for this particular panel? They are 3, 3. So if we're going to check for validity, we need to actually pass 3, 3. So what we're trying to do is always find the coordinates of the upper left-hand corner of the panel. So this is meant to find the coordinates of the upper left corner and what he does to get it is he subtracts off the remainder when you mod it with 3. Okay, so in this case, 5 minus 5 mod 3 is equal to 5 minus 2, which is equal to 3. Okay, so he's just subtracting off, in effect, the offset. There's some offset into here, and what this is doing, this is subtracting off the offset. So he's subtract off the offset, which he's getting at via the mod operation. And that gives him the beginning of the panel. Okay? So questions about that? Okay. So any questions about the Sudoku solution? Okay. In that case, we will move on to the Towers of Hanoi. Let's see if I can actually come up with a quick picture of it. Whoops. He had the Tower of, let's see, just a second, I like that. So Dr. Planck had the Leaning Tower of Onions. Come on, there we go. So facetiously, we need to move all these onions to a different peg. But the actual Hanoi, Towers of Hanoi problem, the idea is that you have some number of, here, this is even better, you have some number of disks. And as you can see, whoops, that's not what I, well, this is fine. So you have some number of disks, and the biggest one is on the bottom, so they go upwards in strictly descending width or diameter. And what we need to do is move this pile to one of the two empty spindles so that it ends up in the same order from widest at the bottom to narrowest at the top. And we're given one additional empty spindle to work with as scratch storage. So that's the puzzle. Okay? And it turns out that the solution is remarkably simple if you think of it recursively. Okay? So we'll do it first. So we'll have our 3 platforms. And here's our disks on the first platform. Okay? So let's first just do it by hand to show you an example. Okay? So one thing I could do is start, and I could move this one over, say, to here. Okay? Because I have some scratch storage. And now, what is my only possible move based on what I've told you thus far? I want to move, well, I have 2 possible moves, but if I want to make progress, I don't want to move the smaller one back to the top. If I want to make progress toward moving this one over to here, what's going to be my next step? Second disk can be moved over to here. Okay? And I will erase this one. Okay? Now, we have multiple possible moves. I could move the smallest disk right here. I could either move it back to here or I could move it over to here, right? Well, I know the way to do it. I'm going to move it over to here. Okay, so I've now succeeded in actually moving the top two elements over to the empty spindle. So actually, let me get rid of this and this because they're not really part of it. So I have a spindle here, and a spindle here. So I've succeeded in moving the top two elements over. So if I'm looking to make progress, it would make sense now that I would move this one over to here, right? Do we agree? So I move that to here. Whoops, too big. And I'll erase this one. And can someone suggest what might be a good move now?
First disk on the largest disk.
First, what's the first disk?
The shortest.
The shortest disk actually moves all, whoops. The shortest disk moves all the way back to here. Okay, so the shortest disk comes back to here. Okay, and that is going to allow me to move this disk over to here. Once I've done that, I can move this disk over to here. Okay, and now you'll see that I've succeeded in moving 3 of them over. Okay, and this also might give you some inkling of a recursive solution, which is I managed to move, I had a stack of 4, and I've successfully moved 3 of them to the middle spindle, right? So now I can move this big long one over to here, and we can be pretty confident that I should be able to now move these 3 over to here. Okay, which it doesn't give me quite. What I was after, but actually it does. It means that I've managed to move them all over to another spindle. So the idea is going to be that if I have n disks, what I would like to do is move the top n minus 1 disks. So move the top n minus 1 disks to an empty spindle. So that's going to be step 1. Okay. Step 2 is then move the remaining nth disk to the other so this empty, so if we have 1, 2, 3, we might move the top n minus 1 disk, say, from 1 to 3. That means spindle 2 is now empty. So move the remaining nth disk to the second spindle. And finally, step 3 will move the n minus 1 disks from spindle 3 to spindle 2. So it's a recursive solution. We first solved the problem with n-1 disks. Once we've solved it with n-1 disks, so conceptually, we start with n-1 disks, and here's disk n. Step 1 is we move the n-1 disks over to here, so that's step 1. Okay, that erases this. Now, we're guaranteed with this biggest disk that we can move it over here, and since it's the biggest disk, anything can go on top of it. So that's step 2. And then step 3 is to move this pile over to here. And we'll be done. Okay? Now you can puzzle over this. I find this one, if you start thinking about it too deeply, you will get confused. It's easier to just think about it at this high level, okay, in terms of these 3 steps. If you try to start executing the actual steps, okay, which Dr. Planck does allow you to trace out, believe me, I think you'll get totally confused. That's what I mean. This is a problem where it's better to look at the forest and not look at the trees. If you start looking at the individual moves beyond a tower of size 3 or size 4, I think you're going to get lost. Okay? But if you stick to kind of the top level recursive solution, it works out pretty well. So the solution is essentially right here. So he has his solver. So he creates a class called Towers that's going to contain the information. So let's see. There we go. Nope. Nope. There we go. So Towers, which is going to be, we're moving n disks. So the int n is the number of disks to move. So n is the number of disks. Okay, and a move is from, this is a spindle number. Both of these are spindle numbers. Okay, so one of his procedures is to move from one spindle to another spindle. The print is to print out his towers. So this will print the towers. So we're calling them, instead of spindles, I guess we're calling them towers. And then he's using a DQ in order to handle it. Seems like he should just as easily use a vector. Why do I think he can just as easily use a vector as a DQ here, based on what you've seen?
Because you just add it to the back.
You're always just adding to the back or to the top of the vector. So in fact, I think a vector would be the superior data structure here based on what we've told you.
What about a stack?
It's, okay, a stack, yes, but a stack is typically implemented as a vector. So I'm just talking about the lowest level implementation of it, right? So you typically, this is a stack, and you typically implement a stack as a vector, not as a DQ. So that's why I kind of double took when I saw DQ here, because that's kind of an unusual implementation for a stack. Okay, because essentially that's exactly what we have here, is we have 3 stacks.
Do you
Okay.
recommend
Yeah, that's personal preference. I think a stack's overkill here. Okay, it's a lot of extra machinery for something that's very. But I see what you're saying. You could use a stack data structure too. Anything is fine. We'll go with the DQ. Okay, so these are our towers. Capital T is going to be our towers that contain our disks. And the size of a disk will just be represented as an integer. Okay, so disk n will be equal to n. Disk n minus 1 will be equal to n minus 1. Disk 1 will be equal to 1. So that's how we're keeping track of the size of our disks. Okay? So, really the only interesting, as I say, I think the interesting thing is the solution. So we'll start with really just solve. So we have an instance of towers. We're moving a set of pieces from one spindle to another spindle, and we're moving that many number of pieces. Okay, so the base case for our recursion is if we have a single piece. It's real easy. Okay, if we just have one piece, we're essentially done. We just move. So if we have two spindles, or two towers, sorry, I always was brought up calling them spindles. But if we have two towers and only one disk left, then it's a very simple thing to move it over here and we're done. Okay, so that's what that code does, is it simply makes a move. This is from, this is to, it simply moves the disk. So that's our base case. Okay, our non-base case is the recursive case. So the first thing we need to do is we need to find the empty spindle. So Dr. Planck calls it other, but this is really the empty spindles. Now it's not the empty spindle, it may have stuff on it. But it's the spindle that we're going to use for scratch storage. Okay, so this is the spindle or tower being used for scratch storage. And since we have three towers, and since from and to take up two of the three towers, other is whatever from and to aren't. So he just has a quick for loop to find what is the so-called free tower. Okay, and then we have, remember I had steps 1, 2, and 3. Okay, so step 1, move the top n minus 1 disk to an empty spindle. So that is step 1 here. So we move the top n minus 1 pieces from to other. That's step 1. Then, when we're done with that, step 2 is move the remaining nth disk to the second spindle. So that's step 2. Once we've done it, we can move the lowest most disk. So this right here is move nth disk to 2, which is our target to 2, which is our target location. And finally, step 3 is to move the n minus 1 disks from spindle 3, which was our scratch spindle, to spindle 2. Okay, so we move it from other, which was our scratch spindle, to 2, moving n minus 1 pieces. So that's step 3. Okay, so a very simple recursive algorithm for solving the problem. And what he's doing is after each move, he's simply printing out what the towers look like after each move. Okay, same thing here. After each move, because if you were asked to solve the puzzle, clearly you would like a detailed set of instructions for solving it. So at each step, he's printing out the exact move you would have to make. Okay, so questions about that? That's essentially just the implementation we talked about. Yes?
Can you go back to the 3-step sheet for a second?
Yes.
Thank you.
And step 2 is this one right here. Okay. Any other questions? Okay. I'm going to erase this. And the other one is his make move. Print. And we'll have to find it. Make move, sorry. There we go. So here's make move, where he's moving it from spindle to spindle 2. So there's a whole bunch of error checking, which we're not too concerned with here. Okay, so he's just making sure you didn't specify out of bounds spindles, you didn't specify that a move from an empty, you obviously can't move a disc from an empty spindle. So if there's no discs on a spindle, you obviously can't move one. And this check right here, he's making sure that you're not moving if you have 2 spindles, let's say like this, you can't move a bigger disc onto a smaller disc. So that's what this check right here is. He's making sure that you're not moving a bigger disc on top of a smaller disc. So the first 4 are simply error checks that, if you do it properly, should never come up. So actually, this right here is the essence of make move. So this is, all this is error checking. And this right here is make the move. And now I see why he used a DQ, because he's pushing and popping from the front. Okay. So he used a DQ because he wanted to push and pop from the front. But it's a stack. I would probably push and pop from the top. Either way works. So the 2-1, he's pushing something, he's pushing the top element from, so this is from, just a second. Let me redo this. So this is from, this is 2. And the way he is implementing it is that his stacks are going upside down. I just don't really like that, but it's the way it is. So he's doing it like this. The smallest one is on top. 1, 2. And then, let's say we have down here something like this. And at any rate, what he's doing is he's moving the 0th element from over to here. He's pushing it onto the... Yeah. He's pushing it onto the front of this, and this becomes 0, and this becomes 1. So at any rate, this is 0, it comes over here, and it becomes 0. And then this pop is popping this one off the top. Okay? So this becomes like that. And then because it's a DQ, everything's going to get automatically reconfigured so that this becomes the new 0 and this becomes the new 1. So DQs work like that under the covers. Okay, so he's removing from the front. If he's using a vector, he'd be removing from the back. And if you used a stack, as Alan suggested, then it would probably be the easiest. So if I was using a stack, this would become the following. So then it would simply be T2 dot, let's see, push T from dot pop, which would be totally elegant. It'd be exactly one operation if it was a stack. So if I used a stack. Pop returns. Nice. Okay. Most reasonable stack implementations, pop both removes something from the stack and returns the value. The STL's brain dead stack may not do such a thing, but most reasonable stacks the pop would remove it and return a value. So this would say remove the top item from the from tower, push it onto 2, which is really elegant, which is why a stack might be the best possible solution if it were a reasonable stack. Okay? But you should understand different ways to do it. The DQ one works perfectly as well. So questions? I'm not going to go over the remaining procedures. I think they're pretty straightforward. You may have to look at them a little bit, but like print, it goes through a whole lot of stuff, and it's just basically trying to print towers like that, where it has a base and then it has the dots being shown. So it does some nice ASCII art, and you can see what happens as the solution goes forward. Okay? So if you want to see the solution in action, you can run it. It's in the notes, and you'll do it. The final thing, just, do I want to cover that now? Sure. So the last thing is that this actually is a fairly expensive solution. Okay? It is exponential. So the number of moves we have to make in order to actually solve an n-piece Hanoi puzzle is 2 to the n minus 1. Can't really do any better, but it's going to quickly get pretty big. So if you have 10 pieces, you're going to be making 1,000 moves. If you have 12 pieces, you'll be making 4,000 moves. So clearly it can take a while. And question is, can we prove it? Okay? The answer is yes. In your math classes, you may have had some experience with recurrences. So if you're trying to count the number of moves, he's abbreviating make move as MM. So the number of moves required for n pieces, well, if we go back and look, we move the top n minus 1 disks, then we move the remaining nth disk, and then we move the n minus 1 disks again. So this 1 represents the movement of disk n to the empty spindle. And then we twice move, sorry, this is the 1, and then twice we move a pile of n minus 1 pieces. So that's the recurrence. That's the number of moves required for n. And the opposite of recursion is induction. Again, if you're not going to get this, don't worry, but you will see it again in 311, which is sometimes to prove something, you can prove it by a process called induction. So we're going to assume that for all values less than n, that this is true. So for all values between from n to n minus 1, we're going to assume that m of, so all I equaled 1 to n minus 1, we're going to assume that this is true. Sorry. Okay, so we'll assume it's true. And now we need to prove true for I equals n. Okay, well, if we make that assumption, we know that m of n equals this. We know that we can substitute in the expression 2 to the n minus 1 for this. Okay, that's our what is called inductive hypothesis. We know that 2 times 2 to the n minus 1 is 2 to the n minus 2. So that gives us 2 to the n minus 1, which proves it. And then we also would have to prove the so-called base case. We actually can't, there has to be some base case, so actually this would be for I equals 2. The base case would be I equals 1. For I equals 1, it says that mm of n should equal 2 to the 1 minus 1 equals 1, which is clearly the case. For a single disk, it requires one move. So we have the base case, and then we have what's called the inductive case. And that's kind of called the reverse of recursion, but you're doing what's called an inductive proof. If you don't understand it, don't worry about it. Again, I'm not going to test you on it. It's one of those things. The professor, when I first got here, used to say that the key to learning is repetition. And why is that? Because the key to learning is repetition. So if you see this often enough, eventually it's going to become somewhat familiar and comfortable to you. Part of the reason for me doing it now is I know that induction and recursion is not something that most of you will find intuitive, and therefore the more times that you see it and your brain has a chance to cogitate over it, the more likely it is eventually to come to peace with it or to come to terms with it. Okay? So again, I will not test you on this, but you will see this kind of inductive proof made in future courses in CS. I'm not sure, in your math classes, have you at any point seen a recurrence like this yet? Nope. Okay. Well, recurrences like this are fairly common in CS, and that's why eventually you take a discrete math class, because this is not something you're typically taught in calculus.
There's some in 312 is recurrence.
Pardon?
I think 312 is where they'll see recurrences. I took
Really?
311 and 312, that's where we saw them.
Interesting. Okay. Well, maybe you'll see it in 312 rather than...
Lots of induction in 311.
Okay, lots of induction in 311, but not recurrences to 312. Well, you will also see recurrences in 140, 302. We may not always solve them, but this right here is what is called a recurrence relation. Okay, it's basically expressing a function in terms of a smaller problem. Doesn't really give you a closed form solution, but oftentimes using induction you can get to a closed form solution. Now you may say, well, how do I figure out what the closed form solution is? You guess. Okay, by looking at it, as you get good at it, you find that there are many recurrences that have the same form, and therefore you can make an educated guess as to what the closed form solution looks like. But that's what it comes down to when you see a recurrence and you want to get the closed form solution. You guess, and then you try to prove that your guess is correct by using an inductive proof. Alan, care to add anything to that? Because quite frankly, that's how I do it, is I make an educated guess based on recurrences that I've seen in the past.
Well, that and the master theorem, and that's pretty much all we ever use.
Okay. We're not going to introduce the master theorem here. Okay. Questions? Comments? Okay. Moving on. You might think, why did we have this interlude with recursion? Well, first of all, you've actually seen some recursion already with lists. Okay, I think I pointed that out, but a list is essentially a recursive structure. If you have a class D node and you have D node star flink, well, that's kind of a recursive definition, right? You're defining D node in terms of itself. So a list is actually a recursive structure. Okay, the base case for a list is base case empty list. And then the recursion is a one element either appended or prepended, either one, to a list of n-1 elements. So a list is actually a recursive structure. We're now going to consider a second recursive structure. Okay? So that's the recursive definition for a list. You'll see that again in a later course, 365, when you get to it. I know that because today I will be going over such a thing in my 365 course. But we will be finding that trees, which are our final subject of the semester, are recursive structures. So, remember that earlier in the semester we talked about trees and maps. And you may remember that I told you at the time that they were implemented as a tree. And I even showed you at the time what the tree looked like, although we didn't go into a lot of detail about it. Okay? But now we are. So first of all, some terminology. Voila, a tree. Okay, this is a so-called expression tree. So Dr. Planck has the expression 5a plus 10b divided by 14 to the a to the fourth minus 28b. And he has created what's called an expression tree. So the top or root operator, that's the root, is division. And then there's two sub-expressions. Okay, so this sub-expression represents 5a plus 10b, and this sub-expression represents 14a to the fourth minus 28b. And you'll see there's a nice recursion here. So in this tree right here, the root is this plus. And then we have two subtrees. Whoops. We have two subtrees. The first representing 5a, and the second representing 5b. I'm sorry, 10b. Okay, same thing over here. Here's the minus sign. Two trees for the sub-expression. This is 28b. This more fancy one for 14a to the fourth. Hopefully you see some recursion here. So the top level tree is recursively composed of two subtrees. Similarly, 5a plus 10b, the plus is recursively composed of two subtrees. So we have some recursion going on here. Okay? You will see that there are nodes that have operators, right? We call these the interior nodes. So in this case, the operator nodes are what we call interior nodes. Interior nodes are nodes that have children, nodes that contain one or more, or that have, I shouldn't say contain, that have one or more children. Okay, and each element of the tree is called a node. So each element of the tree is called a node. And then the operand nodes, okay, this right here, the operand nodes are what we call leaf nodes. Okay, and they have nodes that contain no children. Why is it called a tree? Well, it looks like a little bit like a tree in a forest, right, except upside down. Okay, it starts from a root. I know roots spread out. Forget about that. So, starts from a root, spreads out, okay, branches out. Ultimately, you have leaves. Leaves don't have any branches. So that was the analogy to a real-world tree, just an upside-down one. Okay? Questions thus far? Okay, it is not legal for a node to have multiple parents. So an essential property of a tree is that, and you can see it here, is that no node may have more than one parent. And every node but the root has a parent. Right? If you look at that, every node but the root has a parent. Correct? We agree? Okay, these are just basic definitions. Okay, there are some other definitions. So you'll hear people talk about the height of a tree, or tree height. Okay, and that is the length, or the maximum length of a path from the root to a leaf. So here, the maximum path is either that one or this one. And it is 1, 2, 3, 4 lengths. Therefore, the height of this tree is 4. And you'll also hear us talk about the depth of a node. So the former was a measure of a tree. This is a measure of a node's depth, and it is the length of the path from the node to the root. How many possible paths can there be from the node to the root? Can there be more than one? No. Why? Simple argument. Yes, Sarah?
Each parent only has one parent.
Each node has only one parent. Therefore, at each step to the root, you can only go to one node. So the restriction that each node has a single parent means that there is only one possible path from that node to the root. So for example, if I ask for the depth of that node, it is 1, 2, 3. So the depth of node 10 is 3. Okay, and we have certain default values. So we say that the depth of the root is equal to 0 because we say that the length of the path from the root to itself is 0. And we say that the height of a leaf is 0. And the height of an empty tree is -1. Okay, so if you have a tree with a single node, its height is 0. Again, because the maximum length path, it would be both the root and the bottommost node, so the length of a path to itself would be 0. Arbitrarily, then, the height of an empty tree, to make it consistent, is -1. Okay? And there's some pretty recursive definitions that come out of this. Okay, so if we're looking for the height of a tree, so we'll say the height of a node equals the maximum of the height of any child plus 1. Right? It must be that the height of myself is equal to the maximum of the height of any of my children plus 1. Does that make sense? And similarly, for depth, makes sense that the depth of a node equals the depth of its parent plus 1. Right? Because we are simply then, if we traverse to the parent, so if we go from 10 to the parent, we've added one link, and then however many links it takes for the parent to get to the root, we just add that to that one link to get my depth. So there's some very nice recursive definitions there. Why do I care? Ooh, Lab 10. You will be computing some of this information. Okay? So it will help to know these recursive definitions when you get to Lab 10 next week. So, questions about this. These are basic terms that you really need to memorize. There's no way around it. These are terms that you will hear throughout the rest of your computer science career. Root, interior node, leaf, depth, height, node. Those are things that, subtree. Okay, these are terms that you will hear repeatedly throughout the rest of your computer science career. Okay, so there's a special, okay, then we can talk about tree traversal. So sometimes you need to traverse a tree. And there are 3 types of tree traversals. There is pre-order, there is in-order, and there is post-order. So pre-order means visit all children first, then yourself. No. Wait. Oh, man. Yes. Visit, make sure that's true. No. Okay, pre-order really was. I did get it wrong. Pre-order, visit all children, visit yourself first. Then your children. In order only occurs with binary trees, which we'll get to. So visit left child, then yourself, then right child. So a binary tree is one that has only, where each node has at most 2 children. We'll get to that on Tuesday. And post-order is visit your children, visit all your children in left to right order. And then yourself. Okay, and then your children also up here should be in left to right order. So a couple quick questions. Let's say we wanted to evaluate this expression tree. So we wanted to compute the value of the expression. What order, traversal order, would we need to use in order to evaluate that expression? Post-order. In order to calculate it, you can't perform the division until you know the values of each of its 2 sub-expressions, right? Therefore, post-order is the traversal you would use if you wanted to evaluate this expression. What if I wanted to print it out so that it looks like, sorry, I know it's a little, if you wanted it to look like that, in exactly that way, with the division in the middle, the left expression on the left, the right expression on the right, what traversal method would you use for printing? in order, because now you want to print the left child first, which is 5a plus b. Then you'd want to print the division. Then you'd want to print 14a to the fourth minus 28b. Okay, and finally, for those of you who have seen things that look like division plus times 5a. What's this? I think it's called, is it Polish prefix notation? Reverse Polish prefix notation. Have any of you seen this before? Really? Mark has. Okay, Mark, you're stuck answering the question.
No, I don't know that one.
Okay. Well, there's a form that's called preorder where it starts with the operators first and the expressions last. It turns out you'd have to do a preorder traversal. You'd start by visiting the root, then you would visit everything in your left child, hence getting the plus, then the times, finally the 5 and the a, then you'd get times, and the 10 and the b. That's called, are you sure about this, Alan? It's reverse?
I think that might be regular Polish.
Okay, I think it is Polish prefix notation. And that requires a preorder traversal. Okay, so these are also, these three traversals you also need to memorize because they will be a big part of your lexicon going forward. Okay, Tuesday we shall talk about